Estimating the change in elevation? Yeah, so this is the elevation relative to the border. This is the elevation graph, and this is the rate of change of elevation. So this function is the rate of change of the one that's shown. Okay, or you could say it's the slope, but the scale is highly skewed. So slope probably isn't the best term to use. So we think of the rate of change of this elevation is this function gives that rate of change. And so if we want the change in elevation from 2 to 5, is it? Yeah, so we got this point at 2 miles from the border, and then from 5 miles to the border. So how do we mark up or represent the change in elevation starting from 2 to 5? What do these points have to do with elevation or a change in elevation? Or what about those points? Why? What does this have to do with elevation? I mean, maybe that's what you do, but why do you do that?
The elevation is the y-axis.
Yeah. So the elevation is our y quantity. So we want to know how much does our y quantity change?
You just want to find the distance between the two lines.
Change in elevation. Well, so it's the change in y. Yeah, it's the change in y, right? So from here to here. So it looks close to 200. So about 200 feet that you ascend at over those 3 miles.
So then it would be 200 feet or 200 times 100. Because it says that
Well, that's given in hundreds of feet, but this is given, this says feet, right? This graph says the highway's elevation in feet. $200 feet would be a little too, that'd be pretty steep. Pretty steep. But this graph is given in feet. So yeah, 200. So this being in hundreds of feet would be, I don't know, it might be realistic, but I'm thinking that'd be way too steep. So you could be going up 20,000. Yeah. So you'd be going up 20,000 feet over 3 miles, which is like almost 4 miles. That's too steep. You would go up 4 miles for 3 miles. There's no way. Grade is like maximum 15 or 20%.
really?
Yeah, so that would be over 40. That would be like 50%. Or 50 degrees. 50 degrees grade. If it was to 20,000 feet. So what was the answer then?
So the answer should be
The actual?
Yeah, 206. 206. This is what I'm saying. Yeah, 205, about 206. Okay, we gotta move on.
how do you get that from? Sorry.
What?
I'm a little bit confused. How do you get 205? Divide by 200 by.
No, you have to do the integral, right? So we're gonna use the rate of change function, and that's the last problem, is to use the rate of change function and find it exactly by the integral. Okay, so recall the product rule. It says that if you have a product of functions, it's not the derivative of the first times the derivative of the second, right? It's the first times the derivative of the second plus the second times the derivative of the first. Okay, so if we were going to just do antiderivative across the board here, so we've got the product rule, so we're going to do a technique that's something like undoing this. And so that would mean let's do antiderivative across the board. And so antiderivative of the left side is just you're back to f times g, right? You're back to the original function f times g. And then we have antiderivative of f g prime dx plus antiderivative or integral g f prime dx. Does that make sense? That should make sense. We just take the product rule and we're going to just antiderivative both sides. The left side, we're back where we started, f times g, and then we put this right side. So these problems, what happens is we'll be given an integral, and we won't know this, but if we're gonna use this technique, then that given integral is like one of these two, like f g prime. Okay, and we want the antiderivative, but maybe basic rules, undoing the chain rule doesn't apply. So then we have a hint that maybe it's going to be something to do with the product rule. Okay, so basically, if that's our given integral, then if this is going to be helpful, then undoing the product rule, then this other integral would be easier. Would be one would be more attainable. Okay. And so we want to think of f g prime. So our given integral is the one in red. We want to think of it as one of the terms of the product rule. We want to determine f and g. We'll figure out what f is and what g is. And then we want to compute f and g over there on the left, f times g. And then we're going to compute the easier one, g f prime. And then we can use this equation to solve for the one we want indirectly. See how that works? So our given integral is the red one. If we can figure out what f and g prime is and get f and g, then we can indirectly find the value of this by finding f times g and finding this easier antiderivative g f prime. So then what would the answer be? It would just be f times g minus this easier one. Would be then equal to the one we want. Basic premise, make sense? Okay, so again, here's that strategy. So let's try one here. So if we were given or find antiderivative for x sin x. And so kind of our go-to when we come to a new problem, our go-to is kind of undoing chain rule, the one we did last night. So we look at this. Will undoing the chain rule work? Okay, so whenever think about this for yourself, don't say it out loud. How would you make a small change to this integral so that undoing chain rule would work? So could you write an integral, an alternate integral, making one small change, so that undoing the chain rule would work in that case? Go, everyone do it. Josh, what do you think? Did you go with something?
I'm not.
Okay.
So that
Ian?
Changing the axis within the cosine,
Yep.
so that it'd be to the fourth, and the whole thing divided by 1/4.
So cosine x to the fourth?
Correct.
He wants 4x cosine x to the fourth.
and then spit out cube.
Yeah.
Okay, not a bad first chance, but so what will happen then? Will that... So basically you're thinking here this is g prime f. So then in that case, is this f prime? Does it work?
No.
You want to change it?
I can't think of what to change it to right now on the spot.
Patrick, what do you think?
First thought was adding them, but you can't completely change them.
No.
Yeah, so
We're close. So what's the whole key to undoing the chain rule is this right here. That what's in your inside of your composite has its derivative, or just a factor away from its derivative somewhere else, or the other factor is the derivative of what's in the inside, right? So it's 4x, the derivative of x to the fourth.
2x squared.
What's that?
2x squared.
Well, that would be two changes. We just want to make one change so this works. Brock. Okay, so he offered up this, but this isn't going to work, right? Because what's the derivative of x to the fourth? 4x to the third. Is that what we have? X to the third here? No. So is there something else we could do here so that would work?
Maybe 2x squared.
You want to change this to 2x squared?
No,
Or this?
inside.
Okay, does it need to be 2x squared? Do we care factors? Are we concerned about the 4?
Maybe x squared, and then the 1/8 on the outside.
Okay, so yeah, so the factors, we work out the factors when we do it. It doesn't have to be perfect, right? So we've seen that we make an attempt and then we figure out what factors we need and we make a second attempt, right? So all I was asking was what's something that will work for undoing chain. So you don't have we could put 100 here, 1/5, -6. It doesn't matter, right? The whole point, the key is that this has to be a factor away from the derivative of this. So we need x squared, right? We need x squared. So that when we take the derivative of x squared, then it's x to the first. But you don't have to worry about the 4. You know, we could include 100 here. We could do -60. That works itself out. Factors just come along for the ride.
So we're just thinking about the degree.
Exactly, right. So when we take the derivative, we need the right degree here. So this doesn't have the right degree, right? This is x to the first, and this is x to the first. But we need that to be something of f, where this is f prime, if undoing the chain is going to work. What does that mean? They have to, that when you use the power rule, your degree of f is going to be 1 less than the degree of f prime. Make sense? Or I got the switch, I'm sorry. Backwards. There. Okay. So let's start over. We're doing this one though. So undoing the chain rule doesn't work. So maybe it's this undoing the product rule. So the key is, what is f and what is g prime? So we basically have two choices. Either f is 4x and g prime is cosine x, or f is cosine x and g prime is 4x. Okay, well, let's just try f equals 4x.
Could we guess that f equals 4x because that'll lower the degree to 0?
Right, okay, so he's foreseeing that if we let f be 4x, and then here we're going to have f prime, what will f prime be?
1
A constant, and then that gets rid of this x, and what can be left with something that we can do. So that's right. So he's foreseeing that by making f 4x, then what is f prime? F prime equals 4, right? G prime is cosine x, which makes g equal to sine. And actually, so f prime here actually, okay, no, so that's one. Good. Okay, so this is what we're trying to solve for, so we'll call it A for answer, okay? A for answer. Plus integral of, what's g? sine x, f prime, 4. So here's the question that can help us know if we've chosen correctly at the beginning. Is that an easier antiderivative? Can we do that pretty easily?
Yeah.
4 sine x. Yeah, that should feel very comfortable. We like that a lot better than x times cosine x. All right, and then so then over here, what's f times g? 4x times sine x.
So are we going to solve for this A?
Yeah.
Oh, okay.
That's the one we were given, right? So that's the point that we find it indirectly using the product rule. We don't do that antiderivative directly. We do it indirectly by setting up this as the result of product rule. All right, so then what is A? A equals?
It's just 4x sine x plus
4 sine x minus integral 4 sine x, which is 4x sine x, antiderivative of sine x, negative cosine, right? Negative cosine, but we also have a negative here. So those two negatives become positive. So we have plus 4 plus c. Done. Did you see what happened? Does it make sense? So these undoing the product rule, you're thinking that this was one. So when you do the product rule, you add, you get two terms, right? You get fg prime plus gf prime. So we're thinking that that is one of those. That is one. That's the one that's, say, we call fg prime. And by finding gf prime and f times g, then we can indirectly solve for that antiderivative. So we're thinking that this was one of those two things that was added in a product rule problem. And by finding the rest, we get the value of that indirectly. Questions? Another example? Let's try x squared e to the 3x. Okay, let's practice this other thing. So first of all, does undoing chain rule apply? She wants undoing chain rule, yes. Yes, it does, or it doesn't?
First term's higher degree.
Okay, remember, so undoing chain rule is g f times f prime. So what would, if we were trying to do undoing the chain rule, what would our g prime f be, and what would our f prime? So what would our g prime f be? Would it be x squared, or would it be e to the 3x? What are we looking for? We're looking for a composite function, one function plugged into another. So, Joel, which one? A or B? Joel, your voice changed. Joel. Joel is the person's name. It's Joel. Which one is a composite function? Right. Okay. So then what's plugged into that, its derivative must be the other term. Does it work? Is just the degree. All we need is the degree, right? So derivative of that, is it that, x squared? So how could we change this to make it, what would we need to change this so that undoing chain rule would work? Which one?
The second x, so it drops down to x squared.
So he wants e. You want e to the 3x to the third. Is that what you're saying?
Yeah.
Put a 3 here. He's suggesting put a 3 here. Tyler, what do you think? Agree? Agree with that? Shrug your shoulders. Not sure? Well, what's the deal? What's inside, right? So what's inside the composite function, its derivative must be the other factor. Is that what we have now? What's the derivative of 3x cubed? 9x squared. 9 is no problem. We can deal with factors all day long. So we got x squared. We got what we want, right? X squared would be essentially the derivative of 3x cubed. So if it was x squared e to the 3x cubed, it'd be undoing the chain rule. That would work because it fits this pattern. The interior function, it's the other term is the derivative of the interior function. Okay? But that's not what we have. We have, I forgot, x squared e to the 3x. So now we're going to think, okay, it's a product of two things. Maybe this is one term of a product rule, right? Maybe this is one term of a product rule. So that would mean there would be an f and a g prime. Okay, so we need to either we have some knowledge of which one's f and which is g prime based on experience and practice, or we just give it a shot, and if it doesn't work out, we try the other way. Okay. So let's going with what we did before. What are we going to call f? F would be x squared g prime e to the 3x. Okay, and so what do we need now? We need g, f prime, g and f prime also. So f prime is 2x. G is 1/3 of e to the 3x. Okay, so this in itself is a little undoing chain. Do you see that? This now finding g from this g prime is like a mini undoing chain problem, right? 1/3 e to the 3x. If you're not sure, what can you do to make sure that's the right g? Take the derivative, right? Just like we did. Do your check. Make sure that its derivative is that, which it is. Okay, now we're ready to set this up. This is our answer. Call it capital A for answer, plus integral of g f prime, which would be 1/3 e to the 3x times f prime, and that's 2x. And then f times g is x squared times 1/3 e to the 3x. How do we do? Do we get an easier antiderivative? Is that one we can do?
Yeah.
Other things we can do it. How can we do it? Dima?
Okay, so just move the x squared times 1 to the other side.
Okay.
And the antiderivative of e to the 3x, we know is either 3x. And then
I don't think we
it should just,
Did we find ourselves an easier antiderivative? Kind of. Maybe it's not easy yet, but it is easier. Why is it easier?
We can take another like.
because they're similar.
Can't we just go by parts from here?
Yeah, I can't.
Yeah. So now look. So what happened when we did this? Our new integral was basically the same as what we started with, but instead of x squared, it has x. So what can we do? Do it again, right? So we can take this one and think of this as its own problem and do it again. When we do it again, what will we have? So here we had x squared, and then we'll reduce the degree again, and then we'll just have something e to 3x, which we can handle. So we're gonna do like a sub problem. We're just gonna work on that right there and apply the technique again. So we'll do it in a different color. So now this right here, we're going to start again. And we need an F and a G prime. So maybe let's use new letters, okay? So now I'll use the same letters. Maybe we'll say, let's do capital F and capital G. Just so we don't get, we can keep the same pattern, but we know different now. So what is our F?
X.
So is it 1/3 e to the 3x or 2x?
Well, why don't you just take X?
Sure. X. Okay? Well, then I think it's easier. So then we have to keep track of factors, and we're going to have this is an expression. We're going to have to multiply everything by 2. So I think it's easier to take 2x. Just hold on to it. Then you don't have to worry about the fact that that whole thing is multiplied by 2, and if we find the difference, that whole difference is multiplied by 2. See what I'm saying?
So that'd be wrong.
It's not wrong, it's just inconvenient. Because if you leave that 2 out, you're going to get something like this. Well, then you're going to have to multiply that by 2 and then that by 2.
Was this thinking factor not 2 over 2? Then taking out, finding the general, whatever means that.
I'm confused.
I think it's easiest just to gather the whole thing into parts. Okay, don't factor things out because we're going to have expressions, and then if you factor things out, then all these expressions get multiplied or factored by that number. So just take parts that get that integral exactly. Okay.
These are already in the forms that we take when they're antiderivatives.
Yeah. It's gonna be less of a headache later. Okay, so then our G prime is 1/3 e to the 3x. Okay, so then we need F prime, big F prime, and big G. Big F prime is 2. G is,
1, 9,
we're gonna have another 1/3. 3x. Okay, so now we're on this one, we're ready to go. So we've got, it'll be capital F, G equals, we'll call this B, all right? We'll call this integral B. So FG equals B plus integral G F prime dx. Everyone follow what we're doing? Does that make sense? Okay, so F times G is 2/9 x e to the 3x. So make sure I don't make a mistake. Integral of G F prime would be integral 2/9. So that's the F prime is the 2, and then G is 1/9 e to 3x. So now that one should be no problem, right? And then once we get this value of the integral b, then that will go here, and it'll solve for the value of our original integral a. Okay, so ask me if I lost you. Anyone? You follow? Okay, so b equals be this 2/9 x e to 3x minus this whatever this antiderivative is. So we're going to need another factor of 1/3, right? So 2/27.
That's supposed to be a seven.
227? 27, thank you. We good now?
Do you have to slap a constant on there, or?
We could, but then we're just going to slap another one on the end, so let's just put one on the end. Yeah, so just throw one on the very end. Matthew?
Why is it 27 down there?
Because we're doing the antiderivative of e to the 3x, which would be 1/3 e to the 3x.
Oh, okay.
And then the 1/3 times the 2/9 is the 2/27.
Oh, okay.
Are we good? Yeah, ask. If you're not getting it, probably someone else isn't either, so don't hesitate to ask.
So then we can arrange for A.
So now we can arrange for a. We know what b is. B is the value of this integral here, so now we can say that a is this minus b. Yep. Because to solve for b, it will be this minus that. Moving it over. Yep, moving it over. Exactly. Same thing we're about to do here. A is going to be this thing here, which is 1/3 x squared e to the 3x minus that, which we found over here. 2/9 x e to the 3x minus 2/27 e to the 3x. And now we'll just add our constant here at the end.
One thing I struggle with things where like piecewise integration is losing track of the different steps. Like I find myself drawing big boxes using different papers. So do you recommend we just change the labels like this and keep it consistent? Like I know you went from little f's to big f's, and then you went from A to B.
Yeah, so this is my very best in terms of trying to keep it organized and followable.
It works.
Okay, don't use capital A again, use something new. And then, so use capital letters then for our second go around here instead of the small case. Okay. Other questions?
One question.
Yeah.
For B, we put 2/27. We were taking the integral from 2/9.
Oh, e to the 3x, right? Integral e to the 3x. What's antiderivative of e to the 3x?
E to the 3x. And then 1/3.
1/3. So 1/3. Okay, and so this undoing the product rule is what we use on natural log forms, okay? So whenever you see integrals that involve natural log, not always, I mean, we saw some that were undoing the chain rule, but lots of times, ones that involve natural log that you can't do undoing the chain rule will be undoing the product rule, okay? So let's do one of those. So for instance, just say natural log of 5x. So clearly we can't do undoing the chain rule. Okay? So and just as a basic rule, we don't know what function has its derivative of natural log. Students throughout the ages have tried 1/5x. Is that the antiderivative of natural log of 5x? No, what is that? 1/5x. That's the derivative, right? But you know, it's been tried throughout the ages. Oh, it's this is 1 over 5x. Maybe we need another 1/5 or something, right? Got it. No, but that's the other way around, right? So that's who just took the derivative. Just took the derivative of it.
So this is just our composition, right? We have natural log of something, and then the something is the derivative, right? Like inside the shell. The GF prime.
I'm not.
ln is the derivative.
Yeah, ln of 5x is the derivative of something, and we're trying to figure out what that is, right? And that's not just a straightforward rule that we remember. That's why we need this technique. Okay, so we're going to have f and g prime. Now here we should be able to figure out what's going to be f and what's going to be g prime. Because whatever we pick for g prime, we're going to have to get g, which like is its own little antiderivative. So could g prime be ln of 5x?
Yes.
Then we just be right back where we started, right? Right? Because we'd be needing to find g, but that's what we're saying. We're saying we want the antiderivative of natural log of 5x, so it's not helping. So therefore,
So then you can set
Oh, or G prime is just dx.
yeah, just 1. Yeah. So now f is going to be our ln of 5x, and then g prime is going to be 1. But we also see that making g prime ln of 5x is this puts us right back where we started, because we're going to have to find g, which is the antiderivative of g prime. But that's the problem we have, right? That's the problem we have. Okay, so we're going to get f prime, which is 1 over 5x times,
5.
yeah, not 1/5, right? Times 5. 1 over x. And then g is x. Okay, so here we go. So g times f prime. What's g times f prime? X, yeah, x. That's certainly easy. And then what's f times g? X ln of 5x.
Oh, wow, that's so
So then a is going to be x ln of 5x minus integral of dx x plus c. How can we check our, so on those other ones, maybe on the first one we get, but how can we check our answer? Take the derivative of this, and we should get exactly natural log 5x. So we should do it at least once. Let's do it here. Take the derivative. So derivative of x ln of 5x. First times derivative of the second plus second times derivative of the first, which is then minus derivative of that. So we get x over x and 5 over 5 is 1 plus ln of 5x minus 1 equals this.
So how is the rule composed?
What's that?
How are these rules composed? They start thinking differentially, or they start thinking about integrals? Because you've just shown us it's the same thing back and front. How did it originate, do you know?
Well, I mean, it originates from the product rule. So this is the product rule, undoing the product. That's the whole point. Undoing.
How did the product rule originate? Like, were they thinking about derivatives in the beginning? I guess it makes sense if they call it antiderivative. We don't call the derivative the anti-integral.
Okay. a long conversation for another time. That's a great question.
Sorry.
That's okay. It should be 3. Is that 3? We got one? Okay, here's for your sheets. Okay, you can work together.